Okay, so we're into lesson 9, which is really part 2 of the animation stuff that we're doing. So last week we did animation part 1. Today we're really doing animation part 2. Right, so that's what we're doing. And we're also, for the second half, for the next video that I'm going to do, we're also going to start doing realistic movement, which is almost like a little bit more about physics with Python and Pygame. Okay? Okay, so let's talk about turning sprites a little bit. So we looked at this before, and the difference is here, if you look at the chart up here, you see the angles in math are going to be slightly different than the angles from a navigational perspective, right? So navigationally, you got to go to the right when you start turning, right? Mathematically, you don't go from the right, you go from the left, so up to the left. So everything from a computer's perspective and a mapping perspective starts east. Okay, so if you look at this as a compass, right, and you start doing angles, your initial position on the compass is east. So here's where you start off. Let me see if I can get my mouse going. Over here. So you're starting off at 0. This is east, the easterly position, right? It's not the northerly position like normal navigation, right, where you look in straight up, and then when you want to go 45 degrees to the right, then you would just go to here, and you just turn right, right? So these are the things that are different between regular navigation and math, and when you start programming things, you've got to know the difference when you start turning things. So again, if you're going to go at an angle of 45 degrees, actually what you're doing is you're turning left 45 degrees. You're not turning right 45 degrees. Positive 45 is actually left. Okay, that's one thing to know. So please take a look at this. When you're doing realistic movement and when you start doing angles, this is the mathematics behind it, and it's all done in degrees radian, right? So we're going to look at that later on. Okay, so I like these tips, so we're going to talk about them a little bit more. When you start rotating images, you look at them from a bird's eye view. Okay, so you're rotating the image, and you're kind of saying, okay, what would this look like when I'm rotating this image? Now, this is a very simple rotation. We're not talking about rotating an image with the proper lighting. Okay, so we're not looking at like three-dimensional movement or even a faux two-dimensional, three-quarter down view, where you have something that looks like it has a shadow because that's what the sprite looks like. Okay, that's not what we're talking about. We're saying a very simple sprite that has no shadows. You look at it from a straight, bird's eye view, and then as you turn left or right, you can visualize it a little bit better. And that's why they say the light source should be head on. Now, in more complicated, nicer looking games, when you have a three-quarter down view, you actually have sometimes the shadow as a separate sprite altogether. And we'll kind of look at that today as well as an option. Okay. So you have the shadow as a sprite. You also have, let's say you have a tank. I'm just using a tank as an example. You have the turret as its own sprite, and then you have the base of the tank as a third sprite. So basically your avatar is a multi-image sprite that you put together in layers to make it look good. One of the things it says here, smaller is better, because rotation from a Python perspective is computationally expensive. It is, but in most cases, because our computers are much more powerful these days, even though it's computationally expensive, unless you're rotating a lot of sprites on the screen at once, you're not going to notice the lag, so to speak. Okay, we talked about the default orientation being east. So here's an example. We have these sprite images, and if you look at this spaceship, right, on the screen here, what you have is the default orientation is the spaceship's moving east to the right, right? And if you notice, the bounding box for the sprite is quite small because it's going to bound as tight to the sprite as possible. And then if you rotate the sprite and you do it within Python, it's going to take the pixels and rotate them as much as possible. And if you notice, it does look a little bit wider, right? If you see the box, the bounding box will grow like really much bigger than normal, right? And here's the difference. When you rotate it down or up, as an example, the bounding box from a portrait perspective here, we'll fly into a landscape perspective. So your bounding box and the way your collisions are going to work, if you use a square bounding box, are going to really change. So from when you start building your game, these are points of contention, things that you're going to have to work out. How do I make it so that my bounding box isn't going to grow this big when I do a rotation? Well, there's other methods. We talked about doing a rect ratio. There's a method called rect ratio that allows you to change the ratio of your rectangle that bounds your sprite a little better. Okay. There's other methods and strategies as well. Okay. So let's take a look at. We're going to go into Aptana right now, and I'm just going to launch it. So it's going to be a second. I should have probably done this before we started the video, but anyways. And we'll look at one of the examples. Well, more or less what we're doing is we're going to start rotating things again computationally to the right. And I'm not sure if the code archive is in lesson 9 or if it's in lesson 8, because it's I kind of split it over 2 lessons. Originally, like I said in my earlier videos, this set of animation lessons was all done in one day, and it was a lot to kind of consume for us all, right? So I kind of split them over time. I've learned to split them over a couple of days because it was so they're so intense. There's a lot to go through right here. So let's rotate that pie, I believe, right? Or draw balance, not pie. Here it is. Yeah, I thought it would be here. So let's take a look at this again. We're going to analyze it from a class perspective. And I'm going to keep doing this to you guys over and over again because I think it's important for people who don't understand classes or maybe not a perfect understanding of things. And I'm not going to say that anyone really has a perfect understanding of anything, but the more we analyze this stuff, the more we go over classes over and over again. We're reviewing in some sense, but at the same time, it's an opportunity for you to see classes in a different light yet again, right? So that's what we're going to do. So again, let's look at the idea framework here. Import Pygame. This is the I part of the idea framework. We're going to initiate and import, or initialize and import. And then we're getting into this class. Okay, so the class is called a ship. It is a subclass of the Sprite superclass. We're also going to have a constructor here, and we're going to pass in the screen right here, or the top level window. That's really what the screen is called. You can also name this for your own programming. If you don't like the variable screen, like I mentioned before, you can call it window or top level window, whatever you want to call it. It's up to you as you program. We're also going to pass in this the reference to the top level window to this local or class variable called self.screen. Remember, the self in front of the variable name means that it's a class variable. That's all it means. So it's part of the class. So before the object is instantiated, any class variables are included in the class, right? Then we're also going to include the Sprite superclasses constructor, like we normally do for all of our sprites. We have a variable called ImageMaster, and ImageMaster is where we're going to store the image of our ship. So this is where we're going to use the load method on the image, right? And we're going to actually load this ship bitmap into our ImageMaster. Okay? We're going to convert it to a Python Pygame compatible format, and we're going to copy the master image, this image, into the image variable. Okay, so there's our image variable, a local class variable. And then what we're going to do is we're going to use the image variable, our local class variable, and we're going to create a bounding box using that getRect methodology. We're going to actually define it as a sprite. We're going to put the bounding box outside of it. And remember, when you do the getRect method, what it does is it gives you top, bottom, left, right parameters, and center X, center Y, all those kind of things for your sprite that you wouldn't normally have. It gives you the ability to detect collisions. It also gives you the ability to detect boundaries. We're also going to define, in this particular case, the center of the object as 320 by 240. In this particular case, it's going to be the center of our screen. Initially, we're going to define a direction of 0. Now, remember, direction of 0 from a mathematical perspective or a game perspective is east. So the actual object is going to be pointing to the right of our screen. Okay? That's where it's initially going to start. Our update method, actually we have a few methods here we should talk about. We have an update method, right, which is, this should be old hat for us now. We have a turn left method, and we have a turn right method. Okay, so these are the three methods that we have, right, inside of our class. So in the update method, we define a new local variable called old center, right, and we're going to assign it to the current center of our sprite. That's what we're going to do initially in our update. So again, 30 frames a second, so once every frame, we're going to assign, wherever the actual sprite is, we're going to assign it to this old center variable, almost like a placeholder variable, okay? And then what we're going to do is we're going to perform this transformation that's built into Pygame in Python, right? It's going to allow us to transform, and we're going to use the rotate method of the transform. And if you notice, I'm just hovering over here so you can see it in Aptana. It says the default is surface, comma, angle. So we need a surface. In this particular case, it's image master we're going to use. We're going to rotate the image master, right? And we're going to rotate it the angle of 45 degrees, right? Or sorry, 0 degrees initially. This is our 0 is going to be initially where it's rotated to. So we're going to rotate the image, or we're going to check for a rotation change, whatever the direction change is, every frame. So if I want to rotate my image to the left, every frame I'm going to check to see if my angle's changed. That's what I'm doing, okay? And then, again, I'm going to say my rectangle now, I'm going to reset my bounding box because every time I rotate it, the shape of my image now, my sprite has changed. So I've got to reset my bounding box. If I don't, then what's going to happen is you're going to produce some errors because your bounding box isn't going to be, the center may not be exactly the center of the other object because now you've rotated it, so computationally your center may have changed. Your right definitely has changed. Your left and top and all that stuff has changed. So you have to redo this self.rect. You've got to reassign it or use this method getRect again, right? Okay, and then we're going to say self.rect.center, the center is going to be equal to the old center, right? Okay, this is this key stuff that we're doing. So all we're doing is passing variables along. We're using placeholder variables to change things. And the reason why we did this is because first we reassigned the method. We save our old center here, right? Because this old center has the center of our the old sprite with the old sprite geometry before it's been rotated. Because once you rotate the sprite, your center may shift a little bit, right? And then what you do is when you rotate it, you get your center again, and then you assign your current center now that it's rotated, because you've reset your bounding box, to the old center, the one that you saved. That's all this is doing. Okay, here's a couple of methods. So this is our turn left method, right? So whenever we say, whatever our ship is called, if we say ship.turnLeft, right, then it's going to do it's going to be a bunch of things. One thing it's going to say is, I'm going to change my direction by, I'm going to add 45 degrees or 45 to my direction variable, which is part of my class. And again, remember, computationally, it's going to move the object to the left, right? From east, it's going to go north, in a more northerly direction, okay? If it was facing east. And we're also going to do another thing. We're going to check, and we're going to say if our direction is greater than 360 degrees, well, then you know what? Change our direction to 45 again. Because mathematically, Python may crap out, right, if you're trying to do an angle that's greater than 360, right? So it resets the angle. It goes back to 0, basically, is what it does. So 360 is equal to 0, right? Because 0 and 360 are exactly the same. They're pointing in the same direction, east, right? So beyond 360, it can't understand that. So what it does is it says, well, 360 is actually 0. If we're going to go to 45 degrees, then make it 45, and don't make it so it's 360 plus 45, which would be 405, because 405 doesn't compute as an angle in a circle. Similarly, when you turn right, you actually subtract 45 degrees, and when you check to see if the direction is less than 0, which means it's going to go to the right of east, or in a southerly direction. And again, we don't understand any angles that are negative, so when angles go less than 0, we actually assign it to 315, because we're going to subtract 45 from 360 to get 315. Okay, so these are the kind of checks we do in these two turn left and turn right methods. The rest is pretty similar to what we've seen before. We've got our main function. We're setting our screen to 640 by 480. That's part of our D in the IDEA framework, right? We're going to set the caption, in this particular case, to show sprite bounding box, right? We're going to set the background surface, or this container, which is, again, a container within the top-level window, to the screen size of the surface of our code, or our program, which is, again, 640 by 480. We've defined this screen as 640 by 480, and this background as a surface is going to be equal to the screen size. Okay? And we're also going to say the background is initially going to be filled with 000, which is black, right? RGB being 0, everything off. Then we're going to instantiate the ship, okay, this object, and we're going to pass into it the background object, right? That's interesting because before, if you notice up here, we called it screen in the class. It doesn't care. It's going to take a surface. It needs a surface object where the ship is going to sit on top of. In this particular case, when this program was created, background is the surface that's passed into the class, and so that's what is going to layer the ship is going to actually be layered on top of our background. It's going to belong. The parent of the ship is going to be the background. The ship is actually going to be a child sprite that's going to be attached to the parent. We're going to include the ship as part of a group of sprites, like we normally do in all sprites, right? And then we're going to instantiate we're going to start off our game loop. Here's the game loop right here. And again, clock tick is 30, basically tells us that it's going to be 30 frames per second. We're going to listen for all the events with pygame event.get. That's what it does. It's kind of an all listener, like the All-Father, Odin, right? He's the All-Father, the all listener, for those people who believe in Norse myths. Anyways, I digress. Then we're going to actually listen for the pygame.quit event, which is our X, the X on the top of our window. That's what that pygame.quit event listens for. We're also going to listen for these key down events. One of them is going to be the left key, so the left arrow, and the right arrow. We're listening to these things. And when the left key or the right arrow key are pressed, we're going to actually activate our turn left or turn right methods. So we're going to turn the sprite left to right. Then we're going to actually display everything onto the background. That's where the background actually, it's going to be displayed on the screen at the 0, position, the top left corner of the screen, right? And we're going to clear our sprites. We're going to update everything, every frame. We're going to redraw everything. And then what we're going to do is we're going to say, let's draw a rectangle, right? This is what this is. Let's draw a rectangle around the ship itself. Here's the ship, right? And we're going to make this rectangle a white rectangle. Now this is for illustration purposes. This is why we've done this. With a boundary size of 3. So this is our actual border size. Our border size is 3 pixels, right? And then we're going to flip the display or add double buffering. That's what this does. Let's take a look and see what it does. Okay? So again, there's going to be this white rectangle. Here it is around the ship. This is our ship sprite right here. And if I press the right arrow key, I actually rotate to the right. And if you notice, 2 things happen. My bounding box increases, like we showed you in the PowerPoint presentation. If I shift back with an arrow key to the left, our bounding box decreases. If I shift to the left again, our bounding box increases, and then to the top, our bounding box decreases and also changes shape. So this shape and this shape are totally different. This is portrait, this is landscape, and again, it's going to change the size of our bounding box. Now we can't really move because my up arrow and my down arrow are kind of disabled right now. We're not using them. All this thing allows us to do is rotate, and we're doing this computationally. We don't have different sprites that we're using here. It's one sprite. It's ship.bmp. And again, let me point that out again to you. So I'm not using different images for the ship. I'm using the same image, but I'm using the transform, the rotate transform methodology, right, in my update to change the direction of my ship or transform the object mathematically. Okay? So again, there's issues with this. Okay? And one of the issues when you transform an object as a sprite that you load it as a bitmap, it transforms all of it, including all of its errors. Let me say that again, all of its errors. That means if you have extra pixels that are lying around, if you haven't cleaned up your image nice, when you load up your image and you try and rotate it, it's going to try and translate those pixels as well, which is going to look kind of funny and weird. Same thing with if you have some kind of shadow in an image and you're trying to rotate it, it'll try and flip the shadow too. So it could cause some weird, effects that you wouldn't have expected. So be cognizant. This is one way of doing rotations. There's other ways too. Okay. let's shift this back to the presentation. So in a nutshell, again, we have this ship sprite. We're going to build on this over the next over this presentation. Okay, we kind of covered this, so we're going to move on. And we talked about the ship class, but let's take a look at now rotate.py. All right, so the first one was this other program here, draw bounds, because we're just drawing the boundaries, so you can see this. You can see the boundaries of the ship, how it changes, right? And now we're going to actually go to rotate.py, which is the next program we want to explore. It's going to have the same ship class. We're going to do different things with it, though. Okay, let me bring that up. Here's rotate.py. Same kind of idea, again. Ship class hasn't changed. It's only one ship. Everything's the same. Your update, again, exactly the same as before. Your rotation, same as before. Turn right and left. Okay. In fact, it's pretty much the same code. The only difference is here that we've taken out the bounding box around the rectangle, so you don't know if your ship is rotating. So now it becomes a little bit more clear. This is typically what your ship would look like without the bounding box. So you have a rectangle to show the bounding box here. Okay, that's what this is doing. Okay. And we talked about all this. Updated the rotating ship. We talked about the updating the code and turning the sprite left and right. Reading the keyboard. Again, we're reading the left and right keys on the keyboard. Here's a really cool diagram, and I want to go over this one a little bit because I think this is the kind of stuff that I want you to start thinking about. When you're programming, right, this is a great idea of understanding how to understand data flow, and also when you start doing event handling, let's think about this in a more, more precise manner, if you will. So again, we start off. This is our data flow, right? Our click-through, if you will. The user presses arrow keys, right? The main loop calls the Sprite method, right? So this is almost like an outline, or if you want to call it pseudocode, you can, but it's not really. It's just an outline or a flow chart of how things work, right? And then from there, you have two options, and that's why there's two arrows. So you can turn left or turn right. You change direction. And then in this particular case, we're going to add a couple new methods called speed up and slow down, which actually can increase your speed when you start moving in a direction. We're also going to use this other method called calc vector. We're going to create another program, actually, right, which is actually going to calculate the vector of movement, because once you start adding direction and speed to your movement, when you start changing your angle, there's some more complicated calculations you have to do. So we're going to create a program called calc vector, which we're going to go over, that does all our calculations for us. Then we're going to hit our update. And on the update, that means every frame, we're going to add dx, so delta x, the change in x, or the x position to x. We're also going to add delta y to y, so we're going to change our y as an x as we continue to move. And then what we're going to do is we're going to copy x and y to the rect center and center x and center y of our sprite. Okay? So we're going to add it, and we're going to change our position of our sprite depending on x and y. But we're going to calculate delta x and delta y here in our calc vector program, because we need to do that if we want to have angular movement that looks precise. If we don't do that, then our movement will look really choppy and ugly, right? Like if you change your direction, then you try and move in that direction with your ship. If you don't do it properly, it won't calculate your center properly, and that's why you need to have this extra set of calculations. All right. So let's take a look at move8directions.py to take a look and see how that works. Move8dir.py is what it's called. And again, this code archive is actually in your lesson 8 archive, because we were originally this lesson for animation and rotation was all part of one lesson. Okay, so here's move8directions.py, and we're going to maximize. Ship hasn't changed, right? This ship part, except we've added a couple more variables. Okay, so we have our x and y location, which we're going to assign our center x and center y. We're actually going to have those as placeholder variables, so we know our original x and y locations. Okay, we're also going to have a direction like we had before, a speed, right? So how many pixels we're going to start moving, and X and Y direction, and all of them are delta X and delta Y, so change in X and Y, which are all initially going to start off at 0, which means the ship isn't moving, and it's facing in an easterly direction originally. That's the changes we're making to this particular class, right? The update also has a bunch of changes. We're also calling this this function called calcVector, which we have to look at, right? The method, and the calcVector will actually calculate our delta X and delta Y, and we're going to assign them to our X and Y coordinates for our sprite. Then we're going to check bounds to see if we've gone outside the boundaries of our program. And then what we're going to do is we're going to reset the X and Y, the center X and the center Y of our sprite to the X and Y placeholders that we get from our delta X and delta Y calculations. Okay? Here's our calc vector. All right, so it's a long series of conditional statements. And if you take a look, in other languages, I probably would do this a little differently. Because if you notice, the calc vector is one number. So typically what I would do is create a switch statement in C++, and in other languages. Java is also has a nice that's a nice construct, but Python doesn't have a switch statement. So we do it with if, else if, and else kind of statements, which kind of accomplishes the same thing. So here we're saying is if the direction is 0, well, you know what? Our delta X is 1 and our delta Y is 0, right? So the direction of X, so the change in X is 1, and the change in Y is 0. That means if I'm actually moving in a easterly direction, once I click that easterly button, I'm going to start moving that way. Okay. If my direction is 45 degrees, then delta X and delta Y is 0.7, and these values 0.7 are taken from the Pythagorean theorem. Sorry, x squared plus y squared equals z squared, to figure out the triangle of movement between where you originally started off and where you're going to end up. That's where that 0.7 came from. Okay, Pythagoras. Again, 90. Again, your delta x is 0, and your delta y is -1 because you're going 90 degrees, and from a mathematical perspective, is north. So you're moving 1 pixel up towards the northerly direction, and so on. And if you follow this way, 0.7s and -0.7s and all that, again, we're using the Pythagorean theorem to figure out that 45-degree angle, x squared plus y squared equals to z squared. Okay, especially... Was that?
Seems like a lot of unnecessary code.
There is a lot of unnecessary code. And again, there's ways of changing this a lot to simplifying it. But I think from an explanatory perspective, they're trying to make it so that it's easy to see. So you can see all your angles. But you're right. There are ways of calculating this a little better. You can calculate it and define whether you're going to go, because there's some duplication, like you thought, like in different ways, right? So you can calculate all that a little differently. Okay. Once we find out what the x and y's are, delta x and delta y, what we're doing is we multiply it by the speed of the ship. So if the speed is 0, then we don't care. Delta x and delta y could be -1 or -0.7 or whatever it's going to be. And if the speed is 0, it's going to just be 0. It's going to stop, right? However, if the speed is 1, we're going to multiply, or 5, or whatever it's going to be, we're going to multiply that number by delta x and delta y and move it in that particular direction. Turn left and turn right haven't changed. They're the exact same. But now we have a couple of more methods as well. We have speed up and slow down. And if you notice, in this particular case, our speed up, we're speeding up by 8 pixels, right? So we're saying we're going to increase by 1. And we're not going to allow the ship to move faster than, I like to call it warp 8. It's going to go to 8, and as soon as, if you try and increase the speed beyond 8, it's going to stop, right? And the reason why is because if you move this too fast, remember the angles get really crazy, right? Multiply 8 by 0.7, and you're going to have some weird effects and so on, right? So if you get really, really fast, the faster this goes, the crazier the effects are going to be. And it's the same thing for the speed. You can only cut down the speed in a negative direction by -3. So if you try and go reverse, the fastest you can go reverse is like 3 pixels max, right, per frame. We also have this check bounds method. In this particular case, what are we doing? We're actually saying if self.y is greater than the screen height, right, which is greater than the bottom of the screen, self.y, then self.y is equal to 0. So actually we're doing a wrap. This whole bounding, your check bounds, is wrapping the ship. So as we move off the screen, we're going to appear at the opposite corner, typically. And remember, we talked about it's not exactly a true wrap, the way it works. It's going to wrap according to which x and which y coordinate you leave the screen. Okay. This stuff is all the same. The background is still black. We're still listening for key down events, but we're also listening for up and down arrows now. And we're going to use our speed up and slow down methods when we actually press our up and down arrow keys. And then the rest is the same. We update everything, and we display things on the screen. So let's take a look and see how this runs. So here's a trusty little ship, right? And if I press my up arrow, I'm going to start increasing its speed. There we go. We're starting some motion. If I increase the speed again, if I tap my up arrow again and again, it's going to keep going until I hit a speed of 8. And then it's not going to let me go faster no matter how many times I tap my key. I'm tapping my key a bunch of times. I can also do the down arrow, and it'll slow me down. It can stop me, or I can go backwards, but I can only go backwards at a speed of 3, which kind of makes sense for a starship, right? The Enterprise can only go like minus warp 3, I guess, until Scotty gets into the engines, and then he can make it go a lot faster. Again, we can speed it up until it stops. If we start changing the angle, remember our bounding box changes, and now we're calculating our x and y coordinates with our Pythagorean theorem, because remember, 45-degree angle, you have a right angle, and you can use x squared plus y squared equals z squared to create your angle properly. So again, now we're moving in a different angle, but our bounding is going to be a little different because depending on how we move, wherever our x coordinate or y coordinate is, that's where our angle, that's where we're going to come out. So you'd expect the ship from here to come up back up here, right? But it doesn't. It comes up here because of where we exited the screen. So that's why we have these funny effects. Okay? Reality, if you wanted this, when it exits here to come back here, you'd have to do some funky calculations, some bounding calculations to make it come up there, right? And again, if I want to increase the speed, I can make it increase a lot faster. I can decrease the speed so we can go negative, in the negative direction, even on an angle. And I can change my direction as I go and my speed as I go to control my ship so it looks like I'm moving quite fast. Now here's the problem with this. If you notice, it's pretty choppy, huh? Like if I move 45, all of a sudden, whoop, I'm 45. No ship can turn that fast. I don't care if you're, some kind of alien design, right? In reality, physics just takes over, and if you were to do this, you'd probably have a lot of people dying in your ship, right? Unless you have some kind of crazy anti-gravity or something, right? So trying to keep it realistic, this is a very simple, change in angle from a calculation perspective. Now, you can make it smoother, right? So if every time you tap the left mouse button, you were to move, or the left arrow key, you were to move, instead of 45, you were to move, 5 degrees, that would be a lot smoother, but still there'd be a bit of a hop, right, from 0 to 5 degrees. Okay? And let's just go back there. So really we just handled our 8-directional movement, okay? And then for very simple 2D games, this works fine, right? If you want to angle the sprite, if you have your character and he's walking left or right, your avatar, that's okay. And the great thing is when you do transformations, and I'm going to handle this before we get into animation again, if you re-angle your sprite while the animation is happening, so let's say you're doing a walk cycle animation, right? And you re-angle your sprite so he's going in an angle, well, the whole animation changes, so it looks like he's walking on an angle, right? He might be walking up a ramp of some sort or whatever, and the animation will shift with it. Again, be aware, be careful, because when you start shifting images mathematically, computationally, some really weird, buggy effects sometimes happen, okay? Okay, so we talked about this, how we build a moving ship. This is interesting. I like this chart here. And again, we talked about directional values of 0.7 and minus 0.7. And again, we do that because of, our calculations of x and y come from Pythagoras, right? And here it is, x squared plus y squared, or a squared plus a squared equals 1 squared. Yeah, sure. But at the end of the day, that's how you figure out a squared plus y squared is equal to z squared, and the square root of z is equal to 0.7 when you calculate 1 pixel. Okay? And I'm not going to go through this again. User input's the same, and these are four methods we talked about. Okay, so we've done it with a ship, and now we're going to go back to our mooing cow. And we're going to start moving our cow with a walk cycle east and west and so on. So let's go cow east. And I know this is kind of tedious to go through sometimes, but when we go through at this speed, sometimes it makes it easier for people to understand how it works. Okay, so here's our cow. Right now, remember the cow sprite. I'm not going to go over too much, but more or less the things to note is this. We have here at the top of our class a variable we're defining as east. What's the difference between this kind of variable here, before we have, it's outside of our definition, and we're calling it east in caps, right, as opposed to self.east. What is that? Anybody? Yeah. It's a constant. That's our convention for a constant, and we're actually defining it within our class. Now, this is not necessary. We don't have to really do this. It just defines 0 as east. So from a readability perspective, when we look at our code, remember we talked about readability, and when I do your marking, sometimes I look at some of the stuff you're doing, and I'm like, what is he doing here, right? How come they know this is happening? And the way you can make it more readable is if you use more constants in your code. Like, for example, if you call something east, west, north, or whatever, I know I can calculate the angle of your movement based on these cardinal directions, right, that you're kind of using as constants. So in this case, our cow is going to start facing to the right. Okay, we're going to use our cow stop bitmap image. That's the original location of the original image of the cow. We're going to use this transparent color. We're going to get a selection, kind of equivalent to using the eyedropper tool, in a paint program. We're going to take a sample of our cow sprite of the top left corner, not the 0, 0 corner, but the 1, 1 corner, and whatever the background or the color is of that image, we're going to make it transparent. That's what how transparency works. We're going to use our color key method, set color key, to use whatever that transparent color is, whatever that color we're going to sample as a transparent color. Okay, we're setting the cow in the middle of the screen. We're going to set up this array of images that we're going to use. Right now it's empty, right? We're going to call this LoadPics method, which is going to load up our cow, all of our images, right? We're going to set up this delay, because remember, we need a delay for the cow to bob its head and do its motion and everything else. And typically for our animation to work, we're going to wait 3 frames of a delay between image shifting, right? Originally, we're going to start off, this is another way of doing it, we're going to set the pause equal to the delay, right? So right now our pause is equal to 3. And we're going to say our delta x is going to start walking already, right, at 4 pixels per frame, right? That's what we're going to start. The cow is going to start walking across to the right immediately, okay? That's what it's going to start doing. On our update, we're going to actually count backwards from the pause. We're going to say our pause is minus equal to 1. And we're going to, instead of doing a pause where we actually increase the number to match our delay, we're going to decrease the number until it's less than or equal to 0. And when our delay is gone, we're going to count backwards. Then we're going to actually reset our pause, right? So this is just a way of setting up our delay before we start counting frames. So here's our counting frames. We're going to keep counting until the frames are greater than 7, because we only have 7 frames in our cow animation, right? And then we're going to reset the frame to 0. So we're going to loop into that frame. Okay? And then we're going to load up our images. Self.image is equal to self.frame. We're going to get these images from our image array, and that image array is going to be loaded with images from our LoadPics method, right, which we're going to go over in a second, right? Okay, so here it is. We're going to also change the delta x coordinate, add that onto the center x, and we're not going to really have control of the cow, it looks like. The cow is just going to walk to the right. Okay, that's what it's going to do. Okay, that's why it's called cow east, this program. But really what we're going to do, this LoadPics method is just using a for loop to load up all of our images into our image array. Okay, that's what it's doing. We're going to pass that back into the main class. Okay, the rest of this is very simple, right? We're going to set up a background. Obviously, hex 66 is not a black background, so I'm not sure what that color is off the top of my pointy head. But It's going to, we're going to have a color background where the cow is going to sit. I'm guessing it's going to be green, right? A type of green, right? Because it's RGB, so it's going to be kind of a green color. And then we're going to load our sprite into a group, right? We're going to set up our frames per second to 30, and we're going to listen for the only event we care about is our closing our window. But we don't have any other controls. We can't move the cow right now. All we can do is watch it move to the right. Okay, so let's take a look at how it does that. Okay, we're watching it move to the right. And here it is. So here's our walk cycle. This is a different animation than we've seen before. It's not just the head of the cow bobbing its head. The head of the cow and the legs move as well. And again, these, if you go to Reiner's tile sets, this is where we got the cow, right? And this is how you do that. And if you notice the shadow shifts at the same time as the cow keeps moving right. So this is a typical walk cycle, okay? And if you have a character that walks, you might have a character walking to the right. If you're doing your scrolling, your side scroller, like we talked about over the last couple of weeks, maybe what you want to do is put your cow in the middle, and now your background is scrolling to give the effect, the illusion that you're moving to the right, right? But in fact, all you're doing is you're running this walk cycle without any kind of change in position of the actual sprite itself. Instead of moving the sprite, you're moving the background according to motion, to kind of simulate motion. Now in this particular case, if you notice, this is where I don't like the bounding that's being used here. So as the cow moves to the right, this is another thing you should notice. The cow's moving to the right, moving to the right, moving to the right. And when it gets halfway to the right, so now the cow's hit it, and boom, it pops over here, right? Not a great way of wrapping. There's better methods, much smoother methods than this. And one way is to let the cow actually go off the screen, like its tail and everything, right before it appears, the head appears over here, right? And this is what's happening is they're using the center of the cow as part of the bounding, to do the boundary check. And we can confirm that, all right, on our update, because here it is. If the center of the X is greater than the screen width, then the center of the X equals 0. So, you know, to me, I'm not really happy with that kind of check. You might want to do a better calculation. You might want to say, when, you know, instead of rect center, maybe you want to do rect left. When rect left is equal to the you know, greater than the screen, then what you want to do is you want to say rect right is equal to 0, right? Let's try that. This is a change, right? So when rect dot, you know, the left side of the cow, right, is moving, right? And then the right side of the cow is equal to 0. If we've done this correctly, it's going to be a little bit smoother. Let's take a look and see if I've done this right. So here we go. We get the cow moving. And now I'm going to let the cow go off the screen, right, until the left of the cow is there, and then it's going to start coming back on the screen. That's a little bit smoother, in my opinion, than it's flashing back on, right? So let's watch that one more time. So again, the cow walks, walks, walks. And the right side of the cow, I don't care about the right side leaving the screen. I care about the left side of the sprite leaving the screen. So here it is. The cow's off the screen, left side, and now the right side starts coming back on. A little bit smoother than the way it was written. Okay? You could do that too, but that's much more difficult, right? Because now what you're doing is you're splitting the sprite in two, right?
Or just adding another one.
Adding another one, right? There's many different ways you can create this effect. Yes, you're right. That is the old way of doing it. And but then what you're doing is you're actually peaking almost like, it's almost like there's a time warp. There's a folding of space effect, right? You're walking into the boundary, and when you walk to the boundary, you're actually walking in some kind of dimensional gateway that kind of flashes your body halfway into and halfway out of the other world, right? So it's kind of weird that way. Okay. Let me just change the values back because I want to talk about that with the other class as well. All right. And we'll move on. Okay. So we talked about moving the cow east, right? But now we can build cow.py, right? We want to incorporate the same kind of thing that we got from the spaceship, right? We got the ship. We want to add 4-dimensional or 8-dimensional movement to the cow itself, right? So 8 directions that the cow's going to move. And we also wanted to retain that bloody run cycle or walk cycle, right? Because it's got a walk cycle, and depending on where the cow is moving, it's going to change its direction. So this is what it says here. The hardest part is keeping track of all the images, right? And this is where multidimensional lists are the key, if you will. So let's take a look at that program there. This is a much more challenging program to understand, so we're going to go through it a little bit more in detail. I may take a break halfway through and come back. We'll see how it goes. All right? Again, now in this particular case, we have our constants. This is our convention for constants. We use the capitals, so east, northeast, north, and so on. We've labeled our directions, all right? And depending on where the cow is moving, it has a value. So northeast is 1, north is 2, and so on, right? We start off the same thing, stop 2, right? And the cow is pretty much the exact same way. This time, when we have our image list, right, we created a variable called ImageList that's an array. And let's go into LoadPics before we go into the next part, okay? So LoadPics has changed, right? LoadPics has, it's a file base. And what we're doing here is we're saying, let's start off with different kinds of sprites. So now what I'm doing is, instead of having one sprite that I'm rotating, I'm actually rotating a series of different sprites depending on the movement. So what I've got is a list of images for east, so 7 images for east direction, 7 images for northeast, 7 images for north, and so on, right? And until you have all the images for different directions. Why would you need different images? Why not just rotate the bloody cow? It won't look right, and the reason why it won't look right is because of the shadows, right? The cow has a shadow, and if you rotate the cow, like I said, and you rotate the shadow, it looks like the sun will shift somehow too, which doesn't make any sense. But if you rotate the cow using the image, the actual images are made, these sprites images are made so that the sun's shadow is in the same place. The sun, wherever the light source is coming from the same area, so it makes it more realistic. So now I have, instead of one image that I'm going to be shifting around, I have 8 of them. 8 directions, 8 images. And I'm going to load up, I'm going to do a nested loop, right? Here's the outside loop, right, for the type of list. Here's my list of images I'm going to load in. And here's our file base. Our file base is going to start off which direction I'm going to start loading from, right? And this next piece of code here, this is the complicated piece of code that's going to say, here's our image, and I'm going to build my image. The first part of my image, right, is going to be is going to come from my temporary file name, right? So the first part of my image is going to be like walking E000. That's part of it. The next part of my image is going to come from the frame, right, which is I'm going to put here. I'm going to use interpolation to build my file path. This is my image name. I'm going to use my image name is going to be built upon my nested loop here. Once I have my image name, I'm going to use my load method to load it from the hard drive. And then I'm going to convert it to a Python Pygame compatible file. I'm going to set the transparent color, right, as an example, to the the top left corner of the image, right? And I'm going to append it to my image list, my temporary image list. I'm going to append it to that list, right? So that's how I'm building my images. And I'm going to do this for all my images. I'm going to front load all the images of my cow right up in the beginning. As soon as I instantiate my sprite, I know all the directions, how my cow is going to look when it starts walking. I have my run cycles. I have, instead of one run cycle, I have 8 of them. 1 for each cardinal direction. Okay? This is good, but we're still not quite there in terms of, really awesome, right? Okay, so we've done that with our LoadPics. We're going to go back up here, return control back up to the main class here, right? Here's our LoadPics. We have our cardinal directions. Our original direction is east. We start off with a frame of 0. We have a delay of 3, and we're going to count backwards again with our pause. Our initial speed is 4 pixels, so it's going to start walking 4 pixels, wherever direction we're going to start off. And now here are our dx values that we calculated. This is the thing that you were talking about before, how we can set our dx values right away. So here's our 1 minus, in a list, a tuple, if you will, right? 1, these values are never going to change. 1 minus 0.7, 0, minus 0.7, minus 1, minus 0.7, and so on. it's going to keep on, keep this, the angles, if you will, in this list for dx and dy values. That's what it's going to do. Okay? Then, our update. This is where it gets interesting, right? We're going to use our pause and our delay to, we're going to wait 3 frames for us to shift the images, again, just like we did last time. We're only going to count 7 frames at a time, right? And what we're going to be doing is we're going to go to this calc vector. And this time, our calc vector, right here it is, down here, right? It's going to use our dx and dy values from our list that we created, right? So it's going to say self.dx is equal to the dx values, right? And it's going to be based on the dx value that's part of our direction. So again, if our direction, going back to our direction, right? Way back up here, here's east, north, and so on, right? Our original direction is east, which means our original value is 0. So it's going to look at the first value in our list. So here's our, when we're moving to the right, it's going to have our dx of 1 and our dy of 0, right? That's how it's going to do it. Okay, and so depending on when we change direction, which we're going to see down here in our turn left and turn right, if you notice, it's going to say if self direction is equal to greater than southeast, then self direction is equal to east. We're also going to change our direction by plus or equal to 1 to change which of the angles we're going to use in our list. That's what it's going to be doing. Okay? But anyways, let's go back down to the update. So again, we're going to calculate the vector, and then we're going to change our image list according to this multi-dimensional array. We have an image list that has the direction that we're moving in for the front part of it, as one part of the dimension, right? And our frame as the second part of the dimension. If you notice this, when we say multi-dimensional array, we're also talking about like almost like a row column kind of idea, right? That's what we're doing. So we're going to access or index different pieces of our image list that we've built ahead of time when we when we instantiated our sprite here in LoadPics, right? We've instantiated all our images and we created this multi-dimensional list, right? Our image list isn't just one array or a flat one-dimensional array. It's a two-dimensional array, right? And then what we're going to do is we're going to update, if you will, or increment our x and y positions by delta x and delta y as we've calculated in calc vector. And again, if you look at calc vector, it's much more simple than we had it before because now we're doing all our calculations or our conditional statements up above. Okay? So again, in calc vector, we're calculating the direction based on the dx values and dy values taken from the tuple. Okay, and then we're going to multiply that by speed, just like we did in our previous calc vector, and we're going to change direction of our movement and at the proper angle. Okay, we're going to return control back to this. Okay, so here we go. So LoadPics, and then what we're going to be doing is, again, here are some of our initial values. And in our update, after we do our calc vector, and after we've increased or changed our direction and incremented our speed, we're going to do a check bounds. And this time our check bounds is exactly the same as our last check bounds. Okay, so we're saying if the center x, we're using center x and center y's to move our cow around. So it's not going to be perfect again. You're going to see a radical shift in our cow when it hits the boundaries. It's going to go whoop, and it's going to teleport to the other side again, right? Which is kind of an ugly way of doing it. Okay, skimming down to our main code, this looks like our ship's code, right? Exactly the same as our ship. This time we're calling the actual window cow animation, right? Our window's still going to be green, a type of green, right, and so on. Clock, everything else is exactly the same. And we're also incorporating our left and right values so we can turn our cow left to right. We can't control its movement speed, however. It's going to be locked in for this program. And if you notice, our initial speed is 4. So it's going to move at 4 pixels per frame, right, which is probably a good thing. Okay, let's take a look at the cow and see how it moves now before we pause for a break. All right, so here's the cow. It's moving. It's going to move off the screen. It's going to teleport across. Let's take a look here how it's going to work. Again, it's not going to be the nicest of movements, right? If I change the direction with my arrow keys, now if you notice the angle changes, but so does the light source. The light source stays kind of the same, and so but now we have a different image for the cow as opposed to a transformation. We're not doing transformations here. We're actually loading a different image for every direction, right? So again, here's our, if you notice our shadow now falls. It's going to make sense. It falls from the same light source. Right here it is again. Here's a shadow. Look at the shadow. It's not the same cow. Not the same old cow, right? Here is again, and so on. Here it is here, right? And here's our original one up here, right? Let me just go back. If you notice, the shadow is coming from the back of the cow, right? It's looking like the sun is in its back, right? So that's what I'm saying. This is the advantage of having this walk cycle. And it's a very realistic kind of walk cycle. And again, we're handling 8 walk cycles here for the cow. In each of its movements, it's going to have a different sets of images that are going to be flipping to give that animated effect. Okay. So kind of handled everything in here. We talked about it all anyway. Let's move on and make sure that there's nothing interesting that we want to talk about. Here's our constants we talked about before. Again, capitals being kind of the convention for constants that we use. And this is, I like where they put it this way, in this part of the code. I think they put it at the top of the code, and I think that's where your constant should be. There's also another methodology I've seen with constants, and I recommend you doing this, not just with Python, but also with Java or C++ or Objective-C or whatever language you're coding in. I think it's important to put your constants in another file, right? That way, you can just modify that one file, and you'll see the effects. You don't have to actually touch the code that you're working in, right? So you want to change your constants, you leave them in another file, and you access your constants that way. It's better. Cleaner, I think is the right way to say it. Same thing with these dx and dy values. Theoretically, you could create constants for this 1, minus 0.7, 0, and so on. Like in other words, you can create a tuple, like 1, 0, for your different directions instead of holding them in a list like this, right? That's another option, another opportunity. So when you do your calc vector, it makes more sense. So when I say I'm going northeast, I have everything. I have my tuples all preset in a constant value. I have everything that I'm using, which is the right way to do it. Okay, so there's other opportunities for constants here as well. And again, we talked about this, how what we're doing here is Filebase really becomes our one element or one dimension of our multidimensional array. We're telling you to look at different places in our on our hard drive. And here, as an example, I've said, well, imagine if we had our folder called cow images instead of it being flat, like we have it in our example, right? And we have, depending on which walk cycle you're accessing, whether you're walking east, northeast, or so on, you have 7 or 8 images for each of the cardinal directions you're walking in. So it creates that walk cycle that looks a lot cleaner, a lot better than if you transformed it computationally in the code. Okay. We talked a lot about this, but this is the key here, all right? This format, right, what it does is it's a string format method that's part of all strings. And what we're doing here is we're doing this advanced interpolation that's part of the new version of our Python, right? So instead of using percentage signs for numbers or strings here, we're creating this file path, if you will, by saying it's 0, 1, right? That's our 0 would be the temp file name, which we're getting from, if you notice back up here, here's our temp file name, right? And the second part of that temp file name is the frame, which is it the first frame, the second frame, or the third frame. So you're building up your image list frame by frame. Okay? Okay, and we've talked about the direction. So really, that's all that we're talking about for this particular movie. Let me just go back up here. And we've covered, again, the rudiments of animation, right, from code flipping. We talked about last week. We talked about sprite sheets. You know, we did an exercise last week, and if you haven't had a chance to do it, I encourage you to do this walk cycle for the man that we loaded up last week and so on. In the second half of the class, we ended up doing that. But there's great examples here of how to create some basic animation for your side scroller, if you're going to do a side scroller with a walk cycle, if your avatar is a walk cycle, or if you're doing your main game, your main project that's due at the end of this course. Right? So there's some really key learnings here, and I encourage you to look over these videos and go over these PowerPoint presentations again with the